Well, welcome everybody, and thank you very much for coming along. Believe it or not, this is my last lecture of the academic year. I don't know where... Oh, that's nice. Thank you, Mother. I don't know where the last 6 months have gone, but I'm ready for my summer holidays now. So what I've done this year is to take as my theme some examples of fundamental concepts of mathematics and how they've evolved. And in the same way as last year, I wanted to finish the series of lectures by looking at something applicable or something that was applied. And something that has interested me for a long time is applying mathematics to the population biology of infectious diseases. And I wanted to show you today how we can gain some insights into the dynamics of infections and in particular the effects of vaccination strategies using some relatively simple mathematics. So examples of the diseases I'll be talking about mainly are ones that give you immunity for life, although I'll weaken that towards the end of the lecture. So I'll be speaking about diseases such as measles, mumps, rubella, smallpox and chickenpox. And when I come to vaccination, of course, vaccination is one of the most major medical advances of all time and saved thousands of lives in the UK and millions of lives worldwide. And although it began with the work of Edward Jenner in the late 18th century, it was only in the last century that cheap and reliable vaccines could be produced and that vaccination took place on a great scale. And as you know, the aim of vaccination is to prevent infection happening in the first place and so avoid the need to treat the symptoms of infection. And in simple terms, very simple terms, vaccines work by stimulating the immune system to produce antibodies, but without infecting us with the disease. And the antibodies are substances produced by the body to fight the disease. And the mathematics I'm going to illustrate or use is used in modelling the spread of infectious diseases and then assessing different vaccination strategies. So let me give you an overview of the kind of thing that I'm going to be talking about. We're going to be considering diseases for most of the lecture, which if you survive them, then you have lifelong immunity. And so it's natural, therefore, to divide the population into various compartments. Those susceptible to the disease, those infected with the disease, and those recovered and immune from the disease. And people can move between these compartments, can move between these categories. For example, a susceptible person can become infected, and an infected person could recover and become immune. And also people join the susceptible category, compartment, usually by being born and entering into it that way, although there are various other compartment models that I'll mention later on. And of course, death causes you to leave the population. One of the basic core ideas in epidemiology is that of reproductive rates. And that is needed in order to quantify the transfer from the susceptible compartment to the infected compartment. And I'm going to introduce two reproductive rates, the basic reproductive rate and the effective reproductive rate. The basic reproductive rate is a very useful underlying parameter of the infection. It's the average number of cases that are produced if one infected person is introduced into a population where everybody is susceptible. So there's no limitation of resource in some sense there. So basic reproductive rate is when one infected is introduced into a population where all are susceptible. And different diseases have different reproductive rates, basic reproductive rates, and it's because infections vary in the ease, for example, with which they are transmitted and for the length of time for which a person remains infectious. And the basic reproductive rate can vary between societies due to the nature of social intercourse, social behaviours, and frequency and nature of contacts. Now, by its very nature, the basic reproductive rate is very hard to measure. How can you introduce one person into a population where all are susceptible? So what I want to do is to be able to observe it, be able to calculate it, and I'll calculate it because there's a connection between the basic reproductive rate and the average age at which people get the infection before any vaccination program has started. And it is the intuitively obvious result that the higher the basic reproductive rate, the lower the average age at which people get the infection. And in fact, they're inversely proportional to each other. And the simple compartment model that I'll use will be able to illustrate that result. And in fact, it applies more generally with more sophisticated models. Right. So this allows us to get a measure of the basic infective rate. And in the simple model that I'll set up, we'll see that it mimics one characteristic of infections, namely that they come in epidemics, they come in waves, they come in cycles. And we'll be able to see from the model that I have, I'll use a spreadsheet implementation of it, setting it up as some difference equations, that we can calculate what the inter-epidemic period is and compare that with some actual diseases, and we get pretty good agreement. Right. So in the section on vaccination, I'll give a little background about Jenner. He was an English doctor, pioneer of smallpox vaccination, and often called the father of immunology. And what I'm going to do is to find the critical proportion of the population that is necessary to vaccinate in order to eradicate the disease. And it's a very simple expression involving this basic reproductive rate that I introduced earlier on. It turns out that if we can't achieve this critical proportion in order to eradicate the infection from the population, but we still vaccinate at a lower level, what it does, not surprisingly, is to change the average age at which people get the infection. It raises the average age at which people get the infection. And that might not be desirable, because if you've got a disease such as rubella, and you raise the average age until high enough, rubella is a very dangerous disease if it affects women in the first 20 weeks of pregnancy. So you have to be very careful of the effects, in that sense, of any vaccination thing. And then I want to just finish with something that's a little bit more up-to-date than anything I've done to that part. One of the basic assumptions I'll be making up to this last section, beyond the simple models, is that vaccination essentially is done randomly, and I want to look at some situations in which we can target the vaccination. I also want to look at some situations in which the vaccination does not give total protection, and I want to look at some lessons that may be learned from the 2001 foot-and-mouth epidemic as to how targeted vaccination might help in any future outbreak of that disease. So trying to remove some of the simplifying assumptions and look at something that is a little more realistic. Okay, so let's look at the compartment model. So here S is the compartment of susceptible people, and I'm going to use S as well to denote the number of susceptible people. I is the compartment of infected people, and again I'll use I to denote the number of infected people. And similarly R, the compartment of recovered people, and we'll use it as well to signify the number of people that they have. And this is not surprisingly called the SIR model. And people are going to move from the susceptible to the infected compartment if they acquire the disease, and then if they recover from it, will leave the infected and enter the recovered compartment. And I'm going to assume most of the lecture that when they enter the recovered, they have lifelong immunity. So we need to think of these quantities S, I, and R as varying with time. So they're functions of time. Now, we need to have the inputs and outputs, and we need to have the transfer rate. Now, one of the most important inputs that you can have are births. And here I'm going to denote the birth rate by small b. N is the total population, so add together S and I and R. And the number of births will be the birth rate, whatever period of time that happens to be, multiplied by the total population. So that, for example, in the UK, the birth rate is about 12 per 1,000 per year. So it's 0.012 per person. And if the population we take is approximately 60 million, then that's saying that we're going to have about 720,000 births per year. So that's an input into the susceptible compartment. So let's look at some outputs. And the one we want to take into account, of course, is death. And here I have along the bottom 2 death rates. One, the natural death rate, I'm calling it, which affects all compartments, S, I, and R. And then another one, which will be the disease-induced death rate, and that only is an output from the infected category. So you can see there I've got natural and disease-induced death. And I thought it might be quite interesting to look at one common disease and what it can cause, and that is measles, and to see what the World Health Organization says about measles. Because we don't, I think, in this country now realise just how serious an infection it is. But the World Health Organization, in a fact sheet issued last month, said measles is still common in many developing countries, particularly in parts of Africa and Asia. More than 20 million people are affected by measles each year. The overwhelming majority, more than 95% of measles deaths, occur in countries with low per capita incomes and weak health infrastructures. As high as 10% of measles cases result in death among populations with high levels of malnutrition and a lack of adequate health care. If there's little disease-induced death, we can work with the overall death rate, but bring it in so as to flesh out the notion and the model. In the United Kingdom, the death rate was about 12 per thousand per year in 1961, and it's dropped to just over 9 per thousand per year last year. Well, it's possible to modify the compartment model in very many different ways, and I just illustrate some of them here. You could add a latent compartment that would contain people who are infected but not yet infectious. Tuberculosis might be an example here. And for some diseases, maternal antibodies may protect for the first 3 to 9 months. So infants will be born into a new protected compartment and lose immunity in the first year. And you need to know what the transfer rates are from these new compartments or make assumptions about them. Immunity may be lost and not lifelong. For example, vaccination against influenza. Also, you can build the age structure of each compartment. Not only the fact that somebody is in a compartment, but what the distribution is. What is the age distribution for the people who belong to each of the 3 compartments. And that is particularly important. An obvious example of that is if you're looking at sexually transmitted diseases, the age structure is particularly important. And again, you could divide the compartments into male and female because of the differential effects that diseases can have. And I've already mentioned about rubella and mumps is another example there. We can do all of these things and more, but a lot of what I'll be saying will be true irrespective of how you refine the model according to many of these assumptions. Okay, so I'm just going to stick, just showing you this slide again, the one we had before, with that particularly simple model of susceptibles, infected, and recovered. Okay, let's go to the core notion in epidemiology of these reproductive rates. And we've got the basic reproductive rate, or 0, I've already told you. It's the number of secondary cases produced on average by one infected person when all people are susceptible. And it combines the biology of the infection with the social and behavioural factors influencing contact rates. And here I've drawn from the Centre for Disease Control and World Health Organization some figures as to what the basic reproductive rate is. Measles and pertussis is whooping cough, particularly infective. They will infect in a totally susceptible population between 12 and 18, 12 and 17. And the variation in figures is because they're taken across a wide variety of geographical locations, a wide variety of countries and different patterns of behaviour. Diphtheria, rubella, down half that kind of level, 6 to 7 people on average of somebody infected came into this auditorium at the moment. Polio, a little bit less. And mumps down at the bottom there at the 4 to 7. All right, so. But of course, this is not what happens, because if an infected person is in the population, not everybody is going to be susceptible. There are going to be other infected people. Also, there are going to be people who have recovered and are immune. So that's why we introduced what we call, or I'm calling in this lecture anyway, the effective reproductive rate. So the effective reproductive rate is trying to be realistic. So it's the number of secondary cases produced on average by one infected person when not the whole population is susceptible, but only S out of N of it are susceptible. All right? So you're an infected person in a population where S out of the N are susceptible, or gives you the number of cases that they will produce on average. Now I make this assumption about sort of random mixing or homogeneity, and if that is the case, if I can make that assumption, then there's a very important connection between the basic reproductive rate and the effective reproductive rate, and you can see how important it is because I put a box around it. And it says that the effective reproductive rate is the basic reproductive rate multiplied by the fraction of people who are susceptible. Very reasonable sort of assumption. We can sort of see if it's got the right feel to it. Suppose that everybody is susceptible, so S is equal to N on the right-hand side, then you get R is equal to R0, which is what you would expect. If the number of susceptibles drops right down, then the basic reproductive rate, the effective reproductive rate, is going to reduce. And it's R, the effective reproductive rate, that tells us about the pattern of the disease. If each infected person produces one or more than one on average, then the disease is going to persist. If each infected person produces less than one on average, then the disease is going to die out. So this effective reproductive rate is going to give us a handle on how to vaccinate in order to control the disease. All right. And let me now add that to the compartment model. I've added now a transfer rate from the susceptibles to the infected, and the susceptibles going to the infectives. What have we got? Each infected produces R secondary cases, and we've got I people who are infected, so the number of new infected people is R times I. So we now have a transfer rate from the susceptibles to the infected. We have input from the births and other outputs from the deaths. And that's probably as far as I'm going to refine that particular model. So let me use this now in order to do what I threatened to do earlier on, and to get a way of being able to measure the basic reproductive rate by calculating the relationship between it and the average age at which people get an infection. Okay. And first of all, in order to do that, I want to say a little bit about rates. So this is so it doesn't interrupt the flow of the argument I'm going to go into in a minute. And what you can do is you can make the following approximation. If the death rate is some amount delta per week, then you can show, using sort of probabilistic arguments and making various assumptions, that the average time to death, or the average, same thing, the average lifetime, is 1 over delta weeks. Sort of another example is if you think of tossing a coin with a probability of getting a heads as a half, then the average number of tosses till you get a head is going to be 2, 1 over half. In the same way, if the infection rate is beta per week, then the average time to infection, or the same thing, which is the average age of acquiring infection, is 1 over beta weeks. So I don't want to digress to go into that. It makes certain probabilistic assumptions about things happening independently and so on. But it's a very useful approximation that if you have a death rate, then the average time you'll have to wait to see the thing occurring is 1 over the rate. Okay. So we'll come back and use that in a moment. Let me go to the average age and infection. So going to look at a steady state situation. So the numbers are constant. And if it's in a steady state, then each infected has to produce on average another infected, so that R, the effective reproduction rate, is going to be 1. Now, but remember, I said that the effective reproductive rate R was R0 times S over N. So we now have that 1 equals R0 times S over N. And rearranging that, we get the result, which is important in its own right, is that in the steady state situation, the basic reproductive rate is given by N divided by S, the total size of the population divided by the number of susceptibles. So we have that in steady state. But now let's use steady state yet again. And if we're in the steady state, the number of people who are entering the susceptible population has to equal the number of people who are leaving it. That's what steady state means. But we know that the number of people entering the population is just the birth rate, is just B times N. Right? So therefore we get another relationship. We get that I is equal to B times N. And what I'm going to do now is to use that second relationship for N and put it into the first one. N is equal to I over B. So therefore R0, which from the first box is N over S, I now use the second box to substitute for N, and then I rewrite it in the slightly awkward way. I write N over S as 1 over BS, substituting for N, and I write that as 1 over B divided by 1 over I. This is I here for infected over S. And now I go back to my little aside I had about rates. If you have a steady state situation, the birth rate is going to be equal to the death rate. So 1 over B here is 1 over the birth rate. It's the same as 1 over the death rate. And I told you that that, therefore, is the average age, the average lifetime in the population. Whereas I over S, that's the number susceptible divided into the number becoming infected, and that's the infection rate. And this is 1 over I times S, that's 1 over the infection rate, and that's therefore going to be the average age at which you get infection. So putting those terms in, what we get is that the basic reproductive rate is going to be the average lifetime in the population divided by the average age at which infection is acquired. And various more sophisticated models will give you slight variations on that particular result there. So we see in particular that R0, the basic reproductive rate, is proportional to 1 over the average age at which infection has occurred. And therefore that means that we can now use our tables of the average age at which infection is acquired in order to get some estimates of the basic reproductive rate. And here I've taken tables from one of Anderson and May's publications on the subject. And this is looking at various periods. This is pre-vaccination because we want somehow to get a hold of this basic reproductive rate. And you can see that measles, sort of the average age, 5 to 6 in the USA in the 50s, but looking at other countries with less sophisticated health systems, down to Senegal in 1964, 1 to 2. Rubella, the average age at which it acquired is double that, 9 to 10 in Sweden and the USA. Looking down at chickenpox, polio particularly high, 12 to 17, the average age at which it was acquired in the USA in the middle of the 1950s. And then within England and Wales, whooping cough and mumps around the 5 model, 4 to 5 and 6 to 7. So we now got a way of relating something that we can actually observe, average age, with something that's an underlying parameter within the model. Okay. So let me now turn to how the SIR model can be used in order to explain waves of disease or epidemics. And I had to take some charts which showed it on a pre-vaccination situation and a post-vaccination situation. And I want you just to look at the left-hand side of these two charts at the moment. The top one is measles, the United States. The vertical axis is the number of notifications, and I can't quite make out, I think it's 10 to the 5, per 10 to the 5 of the population. And the bottom one is measles, England and Wales, and on the left-hand side. Looking at that, in both the charts, you see these patterns of disease, patterns of incidence occurring, and there are basically two patterns in here, two periodicities, one of which is the seasonal one between winter, summer, and so on. And then on top of that there's a 2 to 3 year pattern of cycles of epidemic with measles. And for any disease of this particular type, the reason for that, of course, is that the susceptibles gradually decrease as infection is acquired, as people are infected, and then more susceptibles come into the population through birth. So it's not hard to see how the thing can be pumped or driven by this kind of a thing. All right, well, let me try to model and see if we can get this kind of pattern with what I've introduced so far. Okay. And what I want to do is to look at a difference equation model of this. And quite simply, what I'm going to take is S at time n is going to be the number susceptible at the start of week n. I at time n, I of n, is the number infected at the start of week n. So I, n plus 1, is the number infected at the start of the next week, n plus 1. S, n plus 1, is the number susceptible at the start of each week. And I'm taking a period of a week because that's more or less the infection period for measles, the infective period for measles. So, and during that week then, people stay infected for a week and then move into the recovered category. So all that first line is saying is it's saying the number of susceptibles at the beginning of next week, S at n plus 1, is the number of susceptibles we have now at the beginning of this week, plus the number of people that are born during the week, minus the number of people that become infected. So that is all that is being said along that first line there. And the number of people becoming infected is R times I, and R, remember, is R0 times S over N. And then the number becoming infected, I've just described that, at the beginning of next week is this factor R, or R0 S over N times IN. And it's quite straightforward to put this into a spreadsheet where we have here, you have your reproductive rate. Remember, we're able to write that down now because we know it's related to the average age of infection. Then you have your birth rate, 12 per 1,000. You've got your time period in week. Take our population, I took it as 500,000. The initial number susceptible, about 33,000. And then I've got 20 infected people in it. So I have 33,000 susceptible, and then 20 who are infected. And in order to show them both in the same graph, actually, I'm going to divide the number of susceptible by 100. And then what I do is I just use the facilities of the spreadsheet to calculate what they're going to be week after week from then on. And I did this for about 780 weeks, just by pulling it down, which is about 15 years. And what we get then, if we plot a graph of the number susceptible in blue, okay, but in order to get them both living on the same scale, what I've done is not to plot the actual number of susceptible, but the number of susceptible divided by 100. It was just to bring it down so that you could see both of them together. And these are the number infected here, rising up from 20 to 350, dropping down again, rising up again. And if we count the number of peaks that we have here, 1, 2, 3, 4, 5, 6, 7. So we have 7 peaks, more, so that the inter-epidemic period over a period of, what did I say it was, 15 years. So 7 into 15 is going to be between 2 and 3. And it's quite nice in the subject that getting between 2 and 3 is a success for it. Now, what happens if you increase the birth rate, such as you may get in a developing country or something? So we increase this number over here from, let's say, 12 to 36. What you see happening is that the period of the epidemic decreases, and here we have 3, 6, 9, 11, 11 into 15. So it's going to go to an inter-epidemic period of between 1 and 2 years. Now, normally when you see these SIR models, they're couched in terms of differential equations because they want to look at what's happening continuously as things go across. But if you do it that way, you get the same behaviour as I've obtained here by doing it discretely. And I think it's quite nice to be able to see it, you know, when one does the calculations using the difference equations. So there's no qualitatively different behaviour by more accurately modelling it via differential equations. But you can go to the differential equations, which makes the next bit a little bit more easily obtainable, which is to calculate the average inter-epidemic period. And when anybody sort of sees this, the period is equal to 2 pi times something, you think, oh, there must be something like a pendulum in here. And in fact, one of the equations looks very much like the equation for a pendulum. And you can find out that the period is 2 pi root A tau. A is the average age on infection. Tau is the average interval between an individual acquiring infection and passing it on to the next person. So if you do the numbers for some diseases, measles, the average age before vaccination at which you get it is 4 to 5. It lasts, this period between getting it and passing it on is about 2 weeks. And when you do the calculation, 1 over 25 is about 2 weeks, giving a period again of 2 to 3 years. Similarly, whooping cough, 4 to 5. It lasts for a bit longer, 1 over 14. What's that? 3 or 4 weeks. And with rubella, it's 1 over 17, so that's about 3 weeks, giving you the period of these various infections. So the models do explain the inter-epidemic period for these various infectious diseases. All right. So let's now introduce vaccination and see what effect that is going to have. Well, as I've already mentioned, it was due to Jenner, pioneer of smallpox vaccination, and often called, as I mentioned, the father of immunology. Born 1749, trained in London, practiced for the rest of his life in his birthplace in Gloucestershire. And smallpox was one of the greatest killers of the time, particularly among children. And the folklore of the countryside was that milkmaids who suffered the mild disease of cowpox never contracted smallpox. So in 1796, Jenner carried out a now famous experiment on 8-year-old James Phipps. Jenner inserted material taken from a cowpox pustule into an incision in the boy's arm. Jenner subsequently showed that the inoculation of the boy with cowpox gave immunity to smallpox. And initially his ideas met with a lot of resistance, and Jenner experimented on several other children, including his own 11-month-old son. In 1798, his results were finally published, and Jenner coined the word vaccine from the Latin vacca, for cow. This caricature, the cowpox, or the wonderful effects of the new inoculation, 1802, by James Gilray, caricatured recipients of the vaccine developing cow-like appendages. And I think you'll see that cows are beginning to appear from various places. And critics, especially the clergy, claimed it was repulsive and ungodly to inoculate someone with material from a diseased animal. But the obvious advantages and protection of vaccination became obvious, and it soon became widespread. And one of the greatest achievements of public health policy, world public health policy, was the global eradication of smallpox. And this was confirmed by the World Health Assembly on the 8th of May, 1980, when it declared solemnly that the world and its peoples have won freedom from smallpox, which was a most devastating disease, sweeping in epidemic form through many countries since earliest time, leaving death, blindness, and disfigurement in its wake, and which only a decade ago was rampant in Africa, Asia, and South America. Now, mass vaccination as a means of controlling disease has got two main effects. The first, most obvious effect is that those who are immunised are protected against infection. But the second and indirect effect, which is less obvious, arises because a susceptible individual has less chance of acquiring the infection in a partially vaccinated community than in an unvaccinated community. Therefore, there are fewer people around to give you the disease. So it's not necessary to immunise everyone to eradicate the infection, and this is sometimes known as herd immunity. And we can easily calculate the critical vaccination proportion in order to eradicate the disease, which I'm denoting here by this P sub little c. Well, what we need to do, going back to our reproductive rates, is you need to vaccinate a large enough fraction of the population to get the effective reproductive rate or to be less than 1. Okay? But R, we know, is R0, the basic reproductive rate, times S over N. So what you need to do is to make the number of susceptibles to reduce the number of susceptibles so that R0 times S over N is less than 1. You want to reduce the number of susceptibles to make that expression less than 1. So if you need to make the fraction susceptible, just rearranging that, S over N, to be less than 1 over R0. Just a matter of rearranging the algebraic expression. So that's how small you have to make the susceptibles. In order to do that, you have to vaccinate, therefore, a fraction of the population, which is 1 minus 1 over R0. What you need to do is to vaccinate enough of the population so that the fraction which are susceptible drops down to being 1 over R0. So you need to get 1 minus 1 over R0. And that's your critical vaccination rate. And if we look and see what these numbers mean for some common diseases, we've already seen that measles is about 15. We saw it went that range, centred around 15. So the critical vaccination rate, well, if you think of 1 over 15, turn that into your percentage, 15 goes into 100 about 7 times. So 1 minus 7% is 93%. So you need to hit 93% of the population if you want to eradicate measles and whooping cough. For rubella, the basic reproductive rate is 8. So 1 over 8, or turning it into percentages, 8 into 100 is about 12.5. It is 12.5 exactly. So therefore you need to hit 12 or 13 taken away from 100, namely 87% of the population. So certainly for measles and whooping cough, they are very high numbers indeed. And there are the critical vaccination rates if you're able to vaccinate at birth. If you don't, and if you get vaccinated by the age of 2, they go up to about 95% for measles. And in fact, that is the target the World Health Organization has set to eradicate that disease. All right, so here, this gives you a nice illustration of it because it's 1 minus 1 over R0. So the 1 over R0, the shape of that curve is given by this. And if we can find the laser pointer, which we have, one can see along the bottom here the basic reproductive ratio, R0. The critical level of vaccination can be achieved. And as you see, as you go up here, the proportion that has to be vaccinated gets larger and larger. So with influenza, because it's relatively low vaccination rate, its critical proportion is down around about there, just above 0.4. SARS is severe acute respiratory syndrome, which is next. Then smallpox, rubella, chickenpox, and measles. So it's nice to see them all, I think, on the one graph, giving you the proportions that would be necessary in a population in order to achieve eradication. And if we look now at these pictures, these graphs again, but now look at the right-hand side, which is what happened after vaccination was started in a national scale. There's a difference between the policies in the United States and in England and Wales. In the United States, the Childhood Immunisation Initiative began in 1977, although widespread vaccination began much earlier. And it resulted in more than 95% of children in the United States being vaccinated against measles and whooping cough before they entered school. And I think that was enforced by law in many states. And you can see the effect of this strategy when you look along the right-hand side about the pattern of incidence in the United States, where it's dropping off quite considerably. It's always been hard to get that kind of level of immunisation in England and Wales and the United Kingdom. And although it's had an effect, as you can see there, on the number of notifications, it hasn't been nearly as dramatic as it was in the United States. And you also get the fact that after you institute the vaccination, you still get waves of incidence. You still have these regular inter-epidemic periods. And you can see there's a situation where after vaccination has been introduced, that epidemic there is giving you a greater number of infectives than you had during the low point before vaccination. So you need to consider the average number over a period of infection if you're going to properly assess the benefits of it, of mass vaccination. And what I've just done in the next slide is to have some more up-to-date figures from one of the government websites given here. This is the mumps, measles, rubella coverage in England at 24 months from 1992 up to 2012. And let me just give you the main features. It never goes above 92%. Do you remember the figure I mentioned before was 93% if you vaccinated at birth, 95% if you vaccinate up to the age of 2. And here we have in the 1980s, I think that's what, that's not, sorry, this is 2003-04, where it drops to below 80%. And of course, that brings up quite an interesting point that we've seen, because that can give rise to potential conflict between the interests of the individual and the interests of the community. If a vaccine can have side effects, parents might decide not to have their children vaccinated, especially if the risk of infection is low, very low. But the risk of infection is very low only because so many children are vaccinated. And so from the perspective of the individual, it's best if everybody else's child gets vaccinated and not yours. But of course, if everybody adopts that, it leads to the loss of herd immunity and increases the spread of the infection. And we know that some of these diseases can have very severe consequences. All right, I want to look now at the effect vaccination can have on the average age at which the infection is acquired. And vaccination really has the effect of lowering the effective reproductive rate by decreasing the number of susceptibles, and we can show that this has the effect of increasing the average age of infection. And the result is, again, relatively easy to attain, but I've taken you through one example of doing it for the critical proportion. This would be a similar exercise and not of great benefit. I'll just give you the result. The average, if you vaccinate a proportion P, which is subcritical, it's below the critical vaccination rate in order to eliminate the disease, then the average age of infection after vaccination is the average age of infection before vaccination divided by 1 minus P. So if you're only able to eliminate 50%, to vaccinate 50%, you're going to 1 minus a half is multiplying by 2, so you're going to double the average age at which the infection is acquired within the community. So a subcritical amount of vaccination will have that effect. And that could be unwanted. The examples I gave were measles and rubella, where you don't want to increase the average age of infection for women so that they might acquire the disease when they are pregnant. Okay, So you need to think through very carefully what are the consequences of various vaccination strategies. All right. So let me just finish then with looking at some. There was an interesting article looking at some more current issues. The Institute of Mathematics and its Application has a publication called Mathematics Today, and last year, yes, it was last year, they had a special issue on mathematics for planet Earth, and there was a very nice article in it about the mathematics of vaccination by a group at Warwick University. And I just want to take out some of the things that they discuss in that and share them with you. But I should say beforehand that the results I have about the relationship between the basic reproductive rate and the average age, how the average age increases if you don't vaccinate enough, what the critical proportion is, they can all be attained using the more complicated differential equation model. Right. Now, one of the things I have assumed in the way through here is that we have this sort of random mixing. And what we want to look at now is some situations in which we use a targeted vaccination approach rather than a random mixing one. So kind of things I want to look at are 4 other factors and approaches where the vaccines are not perfect, and then how you deal with it, how you calculate using the mathematics of optimizing theory to target in order to get optimal vaccination. Then to have something that, of course, you may have thought of yourself, that population can be thought of as composing of households rather than composing of individuals. So we try to get that graininess into the model. And then looking at a spatial kind of thing, and I'll just illustrate that with foot and mouth, because of course lots of the things I've said apply to other biological situations rather than just infectious diseases. So what ways could the vaccination not be perfect? Well, there could be a proportion that get no protection at all. It just doesn't work for a certain proportion. And in that case, you're going to have to build that in, and you're going to have to vaccinate even more. But more interestingly, perhaps mathematically, it might only provide partial protection in a variety of different ways. So that, for example, it might reduce a person's susceptibility to becoming infected rather than provide full protection. It might only provide partial protection. Or if the person does become infected, it might reduce their propensity to passing on the infection. Or if the person does become infected, it may influence the speed with which they recover. These kind of vaccines are called leaky. But you can build them into the compartment model, because all you do is you add another compartment for the people who have been so partially protected, and then you just have to allocate that to the various transmission rates of going from that new compartment to the various other ones. So the approach of compartment modelling still works. Right. Let's look at optimal vaccination in the situation that the period of immunity offered by the vaccine is limited. If it offers lifelong immunity, a vaccine offers lifelong immunity, possibly after booster vaccines, then the earlier you can vaccinate, the better. But that isn't the case if it only offers a short or limited duration. So 2 examples I'll give you, one of which is the HPV vaccine, which protects against cervical cancer. And it's thought that that vaccine offers protection for 5 to 10 years. So it's important not to vaccinate girls too young, because then the effects of the vaccine will be lost before the age at which they are at greatest risk. And then you don't want to vaccinate them too late when they may have already contracted the infection. And mathematics can help with deciding on how you strike that balance in the impact that vaccination is going to have. And another example is with the influenza vaccine, which provides limited duration of infection because the influenza is constantly changing. And what you want to do is to find out what ages in order to achieve the maximum benefit from it. And I think it's the case that this year, children and young people between the ages of 2 and 17 are going to be included in the seasonal vaccination campaign for influenza. And that's going to have, two effects. It will protect the children and young people, and the influenza can have severe effects for that age group. And secondly, it's also removing a major source of transmission from the population. All right. Well, if you look at households, for example, the mathematics involved in that there is quite interesting as to what you should do, but there certainly was made use of this approach during the recent swine flu pandemic, in which you considered households which had people who were immunosuppressed. And what you wanted to do really was to create enough of a barrier there. You wanted to target those households, and essentially you couldn't immunise the people who were vulnerable. What you do is you immunise everybody else. You vaccinate everybody else within the population. All right. So then my final example then is vaccination in space, and the 2001 foot and mouth epidemic, during which the numbers are quite remarkable. 6.5 million livestock were destroyed, and the economic cost was estimated at 5 billion. And the government, the United Kingdom government, used a policy of culling all the animals in at-risk farms, and this was very unpopular, I think it is fair to say, both with the general public as well as with the farming community. Vaccination was not used during the 2001 outbreak because it wouldn't have been possible then with the resources that were available. But I believe it's now the case that contingency plans for any future foot and mouth outbreak is going to use vaccination as part of the strategy, and they're going to use this ring approach here. There we have red is infected. You're going to vaccinate everybody. Green within a certain range, the light blue circle, in order to protect the susceptibles, which are the darkish blue outside. All right. The barrier or the ring around the infected individual or the infected farm has to be chosen quite carefully, and various mathematical models and computer simulations are used in order to do that. But you have to be very careful to build in, logistical factors, just what is possible into these models. And I've just got two questions written down here. For example, is it possible to vaccinate all cases in the ring on the day that an infectious animal is discovered? Or if there are many initial cases in different geographical areas, is it possible to vaccinate all animals in the required ring around each of them? So these logistical questions are very important to how the thing works out effectively. But in any case, ring vaccination around infected cases, it does have the potential to be of benefit to reduce the impact of future outbreaks of foot and mouth. So in conclusion, really, I hope I've shown you that the use of mathematics can inform and influence the development and implementation of vaccination strategies, and also to see how some relatively simple models and relatively simple analysis of those models, particularly with the use of a spreadsheet, can show some of the actual features that are observed in reality. So thank you for coming today, and I wanted to finish with this, and in the words of Nick Ross of the television programme Crime Watch, don't have nightmares, do sleep well. And I hope now at the end of this series this year of 6 lectures that you are all confused at a higher level. And in order to continue that process of education, do come along next September the 16th this year when I start next year's lectures, and the programme will appear on the Gresham College website and in their prospectus as well. So thank you all for coming.